Hi everybody, this is the next video in Unit 3. This is on concavity and the second derivative test. You can see the objectives here. Be sure and write these down in your notes, your wonderful 2-column notes. We've been talking a lot about inflection points, increasing, decreasing, extrema, and concavity. And so this video is going to fill in some of the notation, some of the rules. You can also find these rules in the book. But I need you to be sure and get the notation written down because that's a very important part of using these first and second derivative tests. So a reminder, what is concavity? Note that the concavity of a function is related to its slope, the slope of the derivatives, because concavity is going to be related to the second derivative. So when we talk about a function graph, and then we talk about a derivative graph, and then we talk about the second derivative graph, we're going to be entering into a discussion of concavity. So you can see the 4 bits here. We have concave up. Notice that it is decreasing. Concave up increasing. This is concave down decreasing and concave down increasing. 4 different states. So the definition says, let f be differentiable on an open interval. The graph of f is concave up when f prime is increasing, and when it is concave down when f prime is increasing. F prime is decreasing on the interval. So remember that a point of inflection is where the graph changes concavity. So here is the official definition from your book. It says, let f be a function that's continuous. Are you hearing the word continuous? On an open interval, and let C be on that interval. If the graph of f has a tangent line at this point, then this point is a point of inflection of the graph when the concavity of f changes from up to down or down to up at the point. Okay, so here is an inflection point going from concave down to concave up. Here's where it changes, right? And it says it has a tangent line at this point. Then it would be a point of inflection. Well, a tangent line has a slope, right? So here's another example. Here's another example, concave. So if this is a point of inflection, then either the second derivative equals 0 or the second derivative does not exist. So remember, we had a similar test when we were looking for extrema, and we were looking at critical values. Remember, the critical value was where the first derivative was equal to 0. And the first derivative did not exist. That was for critical points. Well, a point of inflection is a critical point, but we're going to test it with the second derivative. So here are some examples, and I think I got most of these from your textbook. Noting the point of inflection, here's the graph. This is a polynomial graph, and you can see it's decreasing all the way to here and then increasing, but here's the change in concavity. And so the points of inflection can occur where the second derivative is equal to 0 or the second derivative does not exist. And so second derivative would be like a vertical tangent line or some kind of corner or thing like that. All right, so then here you can kind of see here, this has a tangent line through it, so that would be a change of inflection. This is the tangent of the first derivative. And then here, and then here. Okay, so the second derivative. So notice that the concavity of the function changes at the point of inflection. Note the graph crosses its tangent line at a point of inflection. Okay, and so you can see where the tangent lines are here. Now, you can see here that the derivative at 0, or the second derivative of this function is 0. But 0 with 0 does not change concavity. So it is possible that you could find a critical point, but it failed the second derivative test. So here are a few more notes that I'd like for you to put in there. It's if the tangent line exists at a point where a graph changes concavity, that point is called a point of inflection. This is the concavity changes at the point of inflection. This is a repeat, but it bears discussing one more time. And this, once again, is a repeat of what you've had before. So I changed my mind. You probably have this written down, but if you don't have it written down, here's your second chance. So it says, determine the points of inflection and discuss the concavity of the graph f of x equals x to the fourth minus 4x to the third. So the first thing that we want to do is we want to take the derivative of this function. So I have f prime of x is equal to 4x to the third minus 12x squared. And then we want to go ahead and take the second derivative of this function, which is 12x squared minus 24x. All right, so I want to set that equal to 0 so I can do a test on it. So I'm going to do 12x is x minus 2 equals 0. So my critical values of the second derivative, this is the second because I'm looking at concavity, right, is going to be where x is 0 and x is 2. All right, so these are my possible inflection points, not critical points in terms of increasing, decreasing, or extrema, but we are looking for an inflection, points of inflection, and discussing the concavity. So I'm still going to find test values here, and I'll just use those, right? And put that back into the second derivative. So this is going to be, if I put a -1 in here, that's going to be positive. And when I put the 1 back in, I get negative. And when I put a 3 back in, that's also positive. All right? So on the second derivative, if it is positive in this interval, this is concave up. If it's positive, if the second derivative is positive, it's concave up. If the second derivative is negative, it will be concave down. So this is a test using the second derivative. Okay, so if the graph of f, the beginning function, is concave up on an open interval and the first derivative is equal to 0, then f of c must be a relative min. So I can write that, a relative min of the function. Okay? So let's think about that. If the graph is concave up and the derivative is 0, then this point, C, has to be a min. All right, so let's say this. What if the function is concave down on an open interval containing C, here's C, and the derivative at C is 0, then this must be a relative max of f. Okay? So these are theorems from your book. The test for concavity is just what we did before. You have two states. We say if the second derivative is positive, then it is concave up. If the second derivative is negative, positive, negative, then the function will be concave down on that interval. Right? And I've included a diagram here. So your second derivative test says let f be a function such that the first derivative is equal to 0 and the second derivative exists. It has to exist on an open interval. Then, if the second derivative is positive, there is a relative minimum. If the second derivative is negative, it has a relative maximum. If the second derivative equals 0 and then the test fails, that is, f may have a relative max or min or neither. You might have to rely on the first derivative test, checking increasing to decreasing, decreasing to increasing to determine relative max or min. So the second derivative doesn't always work. The second derivative test might not always work, but then you have the first derivative test to fall back on. Okay, so here's another example. It says use the second derivative test to find the relative extrema for f of x equals negative 3x to the fifth plus 5x to the third. All right, so find the second derivative. So in order to find the second derivative, you have to find the first derivative. So I'm going to find the first derivative, and that's going to be equal to 15x to the fourth plus 15x squared. Go ahead and find the second derivative, which is going to be negative oh, whoops, I forgot the negative on here. Negative 60 x to the third plus 30 x. All right, so I want to identify the zeros. So I'm going to factor out a negative 30x, and that's going to give me 2x squared plus, oh, it'll be minus 1. Minus 1. Now I'll double check. So this would be negative 60x to the third, and then this would be negative times a negative is positive. So get that. All right, so my values are going to be 0, and then if you add the 1, divide by 2, take the square root, you're going to have plus or minus square root of 2 over 2. All right, so we're going to set up a sign chart for the second derivative. So I've got negative square root of 2 over 2, 0, and square root of 2 over 2. All right, and we're putting it back into the second derivative. Okay, so I'm going to pick some values over here, negative 2, this would be negative 0.5, 0.5. You got to be careful because that's 0.7, and then this is 1, so we'll do that. So if I put a negative 2 back in here, negative times a negative is positive, so that's going to be positive. And then if I put in negative 0.5, that's going to be a positive, but still going to be big, so this is going to be also positive. If I put in a 0.5, then that's going to be negative. And if I put in a 1, that's also going to be negative. Okay, so here what we have on the second derivative is that we have concave up here, and we have concave down here. And because it's changing, that's an inflection point. Okay, so that's what we're doing here with the concavity. All right, one more thing. Let's remind us of the house of calculus. Okay, so we always start with the function plus, minus, increasing, decreasing, concave up, concave down. All right, then we move over to and we do the same thing. Plus, minus, increasing, decreasing, concave up, concave down. Move over to plus, minus, increasing, decreasing, concave up, concave down. All right, so if we look at this spot right here, we know that the original function is concave up. We know that the derivative graph for concave up is going to be increasing over that entire domain. And then the derivative graph, the second derivative graph, will be positive or above. Right? First derivative test, we did a lot here. We said if the function's increasing, if the function is increasing, then the derivative graph is above. Right? But on this one, what we're saying, if the function graph is concave up, the first derivative graph will be increasing, and the second derivative graph will be concave up, above, right? So because the second derivative is positive, the function is concave up. If the second derivative graph is below, then it is going to be, the function will be concave down. So this is kind of a mnemonic for putting both the first and the second derivative rules, tests, together, and it's pretty easy to reproduce. So when you're trying to come up with a graph or trying to sketch a graph, this could be really helpful. So be sure that you've got this and can be, just like some of the things we did in trig to help us remember, we wrote it at the top, SOHCAHTOA, or various things like that. This would be really helpful on the next test. So be sure you have this in your notes. And I will see you in class.